Hello, and welcome to this video series. In this series, I want to talk you through the FSI validation using two very popular validation examples or benchmark examples. Actually, we're using the word validation in the wider sense in one of the examples, and the other example is proper validation case. The validation of the fluid structure interaction software we're going to use OpenFOAM, Precise as the coupling library, and Calculix. So OpenFOAM for the fluid part, Calculix for the solid part, and Precise for the coupling. The cases we are going to look at are both similar. We have a cylinder in a flow, and we get periodic vortex shedding after that cylinder. And behind the cylinder, we have a flexible plate, which will move in the changing pressure field or the changing force field that is created by that periodic vortex shedding flow. So you see an example on the right side, which is one of the cases look at. The most popular validation, and validation is the wrong word here, so let's say benchmark case, is from 2006 from a publication by Hron-Turek and Hron. And they proposed this cylinder with a flat plate on a purely numerical foundation. So it is a benchmark case since we do not have any experimental data for it. So in this paper, and I'll put a link in the video notes too. So, and it's on the learning platform for my students. You will see that they tried to get realistically close to some parameters, but it's a purely generic case, so it's not any real material or material property that take into account here. The geometry is a 2.5 meter long channel. It's 41 centimeters high, and we have that cylinder with a flap behind it. The cylinder is perfectly rigid, so that doesn't take part in the fluid structure interaction. It's only the flap that takes part. So the interaction interface, the outside flap. The boundary conditions are a parabolic velocity profile on the inlet. Initial conditions are given with an increase in velocity profile over time, which we can then reproduce in our models as well. We will find all the details to set this up in publication. The material parameters, as I said here, they are realistic in the regime of hyperelastic rubbers, but they are completely generic. So this material combination, but it's not the actual material. So be careful when you read this paper. There's a lot of information in there, and you need to read this paper carefully. Do not. The quantities that are compared are the mean and the amplitude of forces and displacements and the frequency. And we have a separation of the domains in this paper. So what Turek and Ron have done is what you should do as well. They have separated the fluid and the solid and only then combined them. So we have one chapter 4.1 where there are descriptions of 3 CFD tests, which are with a rigid flap. They propose that they set that as rigid by using a very high modulus. In our case, we can simply solve the solid without switching the coupling on, which means it is going to be a fixed geometry. We have 3 cases, all of which have the density of 1000 kilogram per cubic meter. They all have a kinematic viscosity of 10 to the minus 3 square meters per second. So this is actually water. So this is as close to water as you can get. The velocity is 0.2, 1, and 2, respectively, for the 3 cases, which gives us a Reynolds number of 20, 100, and 200. The reason for that is that that Reynolds number is just that regime, or that range of Reynolds numbers, goes across 2 flow regimes. Even for a cylinder only, a Reynolds number of 20 is not supposed to give you a periodic vortex shedding. The plate behind the cylinder, so with a fixed plate behind the cylinder, we discussed that that may inhibit, or will partially inhibit, the periodic shedding of the vortices. So the splitter plate will make this more stable. So, and even with only the cylinder and without the splitter plate, a Reynolds number between 20 and 100 will give you no oscillation on 20 Reynolds number, but should give you oscillation on 100. However, if your numerical method has a lot of numerical dissipation, then the lower Reynolds number will not start to oscillate. So because we have an additional damping in there, which stabilizes the flow beyond what the physics would give us. So it's yet relatively easy to get this oscillating for high Reynolds numbers, but it can be tricky to oscillate at low Reynolds. So the cases here are therefore at 20, 100, and 200 to cover that difficult area. We will see that the cases CFD 1 and 2 will not oscillate with the splitter plate. They say that here. They don't say that actually. CFD 1 doesn't oscillate, CFD 2 doesn't oscillate, CFD 3 at the Reynolds number of 200 does oscillate. And you have the benchmark data in this section. So they looked at this CFD case before they started an FSI case, and I strongly urge you to do that as well. And in your report, you are asked to report on fluid, solid, and on FSI separately. So for the solid tests, what they did is they left that flap, and they set that to in the horizontal, and then at t equals 0, basically gravity was switched on. So the flap will drop from its horizontal and drop down, and then it will start oscillating, at least for some cases. CSM1, CSM2, and CSM3, different parameters, mostly different Young's modulus here. CSM1 and CSM2 are steady state cases. So basically cantilever beam under its own weight. And CSM3 is the more interesting one here, which is the unsteady case. And when we look at the results, we get deformations, which you can compare to your analytical results for CSM1 and CSM2. That's just a steady state deformation. And CSM3, you get displacements. The y displacement is the longer one, that is the vertical direction, the gravity direction. Make sure that you don't set gravity to 9.81. Gravity is set to 2 meters per second squared here. So if you leave that at 9.81, the deformations will be too big. This low Reynolds number, low Young's modulus rubber will not be able to support itself. Full gravity. So here you see the oscillation, and since we do not have any damping effects in there, it's a perfectly elastic material, so it will deflect downwards, and then the stored elastic energy will be recovered and transformed into potential energy, and then go back into into kinetic energy, elastic energy, kinetic energy, and back. So you get an undamped oscillation, and the amplitude should not change time here. That is what you go. That may not be the outcome of your simulation, because if you're too coarse or your time steps are too big, you may not get this perfectly behavior. And then we go into the Fsi tests, and again we have Fsi1, Fsi2, Fsi3, and we have 3 different Reynolds numbers. There's one more difference in these, and that is Fsi2 has a density of 10,000. So this is the one case where the density ratio is not 1. The density in the solid, which is this S, is 1,000 for Fsi1 and 3, but 10,000 for Fsi2. And we discussed stability of SSI simulations, independency of the density ratio, which is here. So beta is the density ratio, that's 1, 10, and 1. So from that aspect, Fsi2 should be more stable. From the Reynolds number aspect, 20, 100, 200, I would expect Fsi1 to not oscillate, Fsi2 to oscillate, and Fsi3 to oscillate. There's another dimensionless number that we discussed in the lectures, E to the rho, E over rho and U, rho F U squared. So that is elastic versus dynamic in the fluid. So elastic and stored energy in the elastic of the solid, and the dynamic or kinetic energy in the fluid. So that ratio here should also tell us if this number is higher, then it will be more stable. However, for Fsi2 and 3, this number is the same. So from that aspect, Fsi2 and Fsi3 are not any different in stability regarding the coupling. However, given this density difference, I would assume Fsi2 to be more stable on the coupling. However, since we have the higher density, we will also get more deformation and larger deformations of the flap, the inertia in the flap, and that may introduce another problem that will cause instabilities, because large deformations mean large velocity of the flap movement. And we have discussed another property or another dimensionless quantity in the lectures, which takes the density, the kinetic energy in the fluid and the kinetic energy in the solid together, which is density ratio. But we can also multiply those two together, beta and AE, give us another dimensionless property that describes the overall stability. Based on that, Fsi2 will maybe different. So there's a bit more than just one dimensionalism. The results for Fsi1, as expected, there is no oscillation, and when you run that case, you will see it starts deviating from the center line a bit and then settles. So no periodic oscillation there. And for Fsi2 and Fsi3, we do get oscillation, and these are visualized here for Fsi2 for both displacements in X and Y. That's the displacement at the tip of the flap, and for the lift and the drag for cylinder and flag. So the lift is calculated for cylinder and flag together. Here for FSI 3, you get similar results, and these are the results that you should then compare your results to. They are then also listed in a table, and on this table I want to go into what is the different level here. When you read the paper and go back a few sections, you will see that there is a mesh refinement being done. So level 2, 3 and 4 are different levels of mesh refinement, and this table also has different time steps. So what Turek and Hron have done here is a convergence study on both mesh refinement. The finer the mesh, better the result, theoretically, and also on the time step. Smaller the time step, better accuracy time. And we will learn how we can use this convergence data to quantitatively assess the error or the discretization error, come up with an estimate or a better estimate for where the real result would lie in. But this is subject of another video. I'm going to discuss the grid convergence index. So this is the first case that I want to show you, and that's the main case we're going to look at in the beginning. This is, as the Reynolds numbers show, a laminar case. The other case is an actual validation case, and you will find a paper on this as well. This is also linked in this website. I will put the link of the website. The link on the website is on the learning platform as well. You'll also find that in video notes. It's the Ackoftac validation database here, and Ackoftac is a research community that has one of the special interests of this research group, research community, is validation, and they collect in the validation test case database different cases that you can use to test your numerical codes and your numerical models on. So UFR 213 is now a fluid structure interaction case in turbulent flow. Turek and Hron, Reynolds number of 200 is laminar. We now have a turbulent case. And what is also interesting here is we have experimental data that we can compare to. So the test case looks very similar. The dimensions are different, but we can convert one case into the other. And the big thing here is that these data come also with experimental data that were obtained in a water tunnel. So here we see that the water flows from top to bottom. So the gravity would be in X direction here. So if you think about adding gravity to your simulations, take that into account. And here we have plenty of results, and I leave it to you to read all of that in detail. The 213 case is the first mode, and we may look at modal analysis as well. So this is the first part of this. Second part, different themes. But when we look at instabilities, we will typically see that at some point they change a bit, and the first and the second mode. So there is a difference here. When you read this paper, this is a very expensive simulation, because what has been done in this paper is a large eddy simulation. We're not going to do that. So if we're doing this case, we're going to do it quasi 2D as well. And we're going to use a runs model for that simulation. So you should now have a closer look at these publications, and I will be back with more detail how we can deal with those, how we can set these up. We will go step by step based on a template that I've set up for the Turek Ron or Hron-Turek benchmark, and then from there you will be able to move that over to the QNet or Ackoftac test case. So that is my introduction finished, and I'll be back with walkthrough template case setup of these cases.